Maybe in interest of time, Behnam, if you can share, and please, Holger, if you can then just give instruction to Behnam when to move to the next slide. We have a lot to cover today, so and I know that experts are busy to devote some time this afternoon. So please, Holger.
You may have dropped off and come back in.
Maybe Behnam, if you would like to.
Yeah, I can start, and let's hope that Holger's technical issue gets corrected. Yeah, from our side, also thanks a lot for keeping us on board and having the invitation extended to the second phase of the project. I'm also very personally happy to see some familiar faces in this meeting, and I hope that everything goes as the first phase and we will have a fruitful cooperation. If Holger is not back, I start the presentation.
Okay, I'm back now. I'm back.
Great. Holger,
Okay.
floor is yours.
No, you have to click whenever I say click. That's why I didn't want to do it this way. Started. Let's talk about the essence of energy modeling. Why do we do modeling, and what is sort of the expectation? And
please mute.
Yes.
You have to click. Yeah. It's not animating.
Do you see now the?
I see only the blank screen essence of energy modeling. Now you have to advance one by one.
The whole thing on the screen now, though.
We're seeing
it. The image and we have the bullets.
Yeah.
Holger, if,
okay.
If you don't see my screen, okay.
Okay. We all know that energy has to serve a purpose. It's not an end in itself. And for that reason, we have to really look at the full system from resource extraction through the whole conversion and transmission and transportation distribution, all the way to the end-use conversion and the energy services. That is the essence of energy systems modeling, that you look at the whole picture, just a slice of it. And that means we deal with a relatively complex system. We have to account for technologies, infrastructures, all these things, not only as a sort of singular shot. We have to look at the vintage, at the performance, how it has changed, what the lifetime is, and all these kind of things with all the constraints and policies and so on. In energy systems modeling, as we do it at IASA, and Behnam will talk about this in a bit, we have to ensure that demand is always met in an efficient way and now, of course, also sustainably. So there is one basic equation that means supply will be larger or equal than demand. Next, Behnam. Click. So, okay. The modeling also has to identify the most important drivers of the system and with a quantification of the interrelations. What do I mean with that? We have to say this energy system is driven by demographics, it's driven by economic activity, it's driven by technology change and innovation, it's driven by policies and all that. And each of these is not an independent, but also interrelated. And that, oops, I'm afraid that doesn't work. Back now.
Yeah.
Go back. Okay. And most important, what I want to say is really Modeling enables transparency. We do a lot of assumptions. Assumptions are usually not seen by the user of the model result or the policymaker or the decision maker. Modeling requires you to quantify. That allows the assumptions to be transparent. You can reproduce model results, repeat it, can explore different futures. Modeling is extremely helpful when it comes to communication and stakeholder involvement. Have you looked at that? Like, you can go back and yes, here my model did look into it. We can test hypotheses and policies and sensitivities and so on. But the model does not predict the future. But we can explore with modeling different future and options which help us to make plausible and reasonable decisions. Next slide. So models are not crystal balls. You can't just take a model and it will give you an answer by saying, hey, what's going to happen with the oil prices in 2030? But models are simplified mathematical representations of real-world energy systems and the relationship between, and calibrated with historical data. So the model is always calibrated to what we know, and then we have to add the scenario, what we want to know and what will happen. So the assumptions, models are assumptions, and we have to parameterize. Assumptions are integral part of the model design. Future rates of technological development are extremely important. Socioeconomics, policy change, all these. That in the end, we all put together and into the model. And the model itself contains the rules, the equations, and all the other technical things, constraints, and so on. And the scenario output then is a combination of the scenario assumptions and whatever the mathematical approach brought up. They are the two sides of the same coin. So the yellow parts up there, demographics, productivity, and so on, and the green parts, which are outputs from the model, they are in the end one and the same. They cannot be separated. They are part of an iterative process. And that's where, for example, we need the input from experts like you folks listening to this. When we come up with assumptions that may help us, please. And then when we have to evaluate results, how are they plausible, reasonable, and so on? How do we best change the assumptions and come back? So the assumptions to the left are quite often shaped by the output from the model. You go back and say, no, that can't be. Maybe my assumption was not rational. So models can inform policymakers on the implication of proposed domestic or international policies, but it cannot say what is the best without having these assumptions readily in your mind. So I guess I'm done for the moment. I will now pass on to the one who has been controlling the slides anyway, Bechnam. He will now make a short introduction to the model that we use. It's the IASA's message model. And without further ado, Bechnam, you take over.
Sure. Thanks a lot, Holger, and my apologies for some technical hiccups. I guess I just quickly give an overview about the message model, which will be the tool being used in this project. Probably most of you are familiar with message. It has been a global integrated assessment model being in use since early 80s, since mid 70s and early 80s. It has been used by different organizations, even for country level modeling like IAEA and IRENA. It's a systems engineering dynamic cost optimization model, and It has been used by IPCC reports and other policy and scientific forums for different types of analysis. And I guess by saying that, I want to remind us that, as Holger mentioned, models are tools, but what makes a model being reliable and being useful is to have a continuous development, have transparency, and having use the model in different purposes, vetting, calibration, and understanding the limitations and strengths of that model. And I guess maybe a little bit more about how the model works. In principle, it's a message is a process-based integrated assessment model. And what it means is that as the input to the model, we define the energy system structure, including what available plants and capacities and equipments we have in a given system, what energy balances, energy flows are in the system. We define demand and techno-economic characteristics of different technologies, cost data, technology efficiencies, capacity factors, and also different growth rates and different policy constraints. And as Holger nicely showed us, this goes to the machinery, it goes to the model. There is a network of different technologies connecting different sectors, and then we have the output. And if you look at the output here, you will see that these type of models are being used for long-term planning. And by long-term, I mean, for example, until mid-century, until the end of century. So we start from today, we define what available options we have, and then what constraints, what limitations, what potentials, what resources we have for the rest of the modeling horizon. And then we run the model and we look at the output, which will be energy mix, share of renewables, electricity mix, emissions, prices, and other indicators and metrics that we can define based on the output of the model. And talking about technology data, I guess this is the place that probably we will talk a bit more details today. Just I want to give you a shot that these are the data that usually will be very useful for us, given the heterogeneity of the UNECE subregions and having different groups of technologies, processes. Is very useful for us if, for example, in your institution, in your agency, in your country, you have, for example, recent reports, recent data that it hasn't come out or it hasn't been public yet, or we haven't found that, it will be very useful to share with us, and we fine tune, we refine the input assumptions and data and try to make the things as much as possible up to date. And for the UNECE project, just maybe a short note for those of you who were not with us for the first phase, we use a global model. It's a global integrated assessment model. And for that, we have different regions. And for this specific project, for the phase 2, we have a new region also, which is Southeast Europe. And these are the geographical resolution or spatial resolution of the model, and the way that we have represented different countries and regions here. I guess given the time, I will leave more details if there were any questions related to the model, and I probably, if Eva, is that okay? I pass it to Francesco to talk a little bit about one of the sectors that is out of interest of the second phase, which is hydrogen.
Thank you. Yes, thank you, Becknam and Holger, for giving this overview how message model works and what's really the essence of energy system modeling. Maybe before we start looking at and addressing the technologies where we identify gaps in our last exercise, hydrogen, CCS, nuclear energy, maybe if somebody would like to ask any question on what you have heard now, so please use chat or raise your hand function. Yes. I have to, is it Jim Rob? I cannot scroll well, so please just turn on.
It is,
Yes,
Beth. Hi, it's Jim Robb from the U.S. Just a question. I'm not familiar with the model, which is fine. Does it do you have embedded in it, or does it have embedded any operational restrictions on the resource selection that it predicts, or are those assumed away? I'm thinking, like, does it test for voltage, for example?
No.
Frequency? No, it doesn't do any of that kind of stuff, right?
No. What we have, of course, we have load curves and so on, but it will not do anything of the electrical engineering detail that is necessary at one point, but not at that planning stage.
Okay, that's fine. That's what I figured. I just wanted to check. Thank you.
Okay, thanks, Jim.
Thank you. So I see that Mark Howitt wants to ask something. So please turn on your camera because now I cannot coach for chat. So Mark and then King Lee. And then Grant. And then maybe we can, unless there are more questions. So Mark Howitt, King Lee, and Grant.
Yes, Mark here. Your model, from the sounds of it, models the inputs and the outputs of the electricity system. Does it model the wires of the electricity system, the high voltage wires? Because, for example, all sorts of different assumptions make very different network costs. There is a big assumption, for example, in the European Union, that you balance lack of generation due to weather in one corner of the continent by surplus generation in another corner and interconnectors between them. Taking the European Union as an entity, that would mean that you'd need to build massive 2 or 3 times over capacity of generation of each of the renewable technologies in every corner of the continent. And you'd have to build somewhere between 50 and 100 gigawatts of interconnection going from every corner of the continent to every corner of the continent, which is a very different cost model from if you are storing the electricity to provide that balancing service.
Okay, first of all, it's not just electricity model, it's a full energy model. We have all the other energy forms and sector and so on involved. We have oil refining for the transport sector. We have power to X for future chemical fuels and so on. That's part one. So it's much more than just electricity. Now to your question, yes, we have through the load curve, a differentiation of availability and capacity use. So for the same output in terms of kilowatt hours or terawatt hours, you will see completely different schedules and requirements if it is done by intermittent renewable or is it done by base load power plants and so on. We do not have, of course, the voltage and this kind of consideration, but the way things have to be sort of organized within the energy system and particularly the electricity system, these are included. And you will see, if we have time, Bechner may show just one the comparison in terms of generation between a business as usual and a called it at the time P2C, I mean Paris to 2 degree scenario. So these things and the investments are all covered, but not at a detail that you would expect for a utility to build such systems.
No, the reason I ask this is because it has a very, very big difference in the cost of the energy transition. So the United Kingdom has just put out a couple of months ago a requirement to build an additional £16 billion worth of grid to accommodate 17 more gigawatts of offshore wind. And the only reason they need to build that is because there is not storage in between the wind and the grid, providing the balancing and the stability services. And so that immense cost is the difference, can be the difference between the energy transition being affordable and it being unaffordable.
Correct. And we have covered this in the model, not as is probably a sufficient detail an expert in this kind of business would expect, but it is considered in the costs and in the investment schedules. So we have investment in infrastructure, that means electricity transmission, pipelines, and so on.
Fantastic. I see maybe that King, your comment was already addressed directly by Beckham, unless you would like to get more clarity. And I see that Grant was comment was actually reflection and comment. So unless you would like to get direct feedback, more feedback from Beckham and Holger, Grant and King, I would suggest that we
No, I'm
proceed.
fine. I'm fine either.
Yeah,
That's
okay,
great.
thank you. I don't know, King, are you happy? And Dennis, are you, maybe if you want to comment something, Dennis, I cannot now track, sorry, your comment. So you can just speak, Dennis, please.
Sorry.
Yeah, my question.
Okay, I think King wanted to say something. Yes, King, and then Dennis, please. Yes, King.
Okay.
Just further to mine and the previous discussion, I just wondered, obviously, there are going to be a number of different scenarios going to be model from your previous slide with particular emphasis, apart from a reference scenario, a scenario maybe with emphasis on CCUS, hydrogen and nuclear. I just wondered, what's the overall insight that we want to get out of the broader modeling exercise here? Because just previous question, about the shared social pathway, are we going to look at a different pathway, the degree of overshoot, and the endpoint, is it 2 degrees or 1/2 degree? So I welcome sort of some as well as different technology that can be played and the emphasis, but what are the overall insights that we want to get out of this from a broader UNECE point of view, availability of technology, and so forth. I just welcome sort of your Holger's thought from a modeling point of view, and also from perhaps the task force here.
Well, my quick reactions, and maybe Scott or Iva should also say respond to it. From a modeling point of view, we want to see how can we get to carbon neutrality. There are definitely different ways with different implications and different costs. It may be affordable, it may not be affordable, and that's what we want to delineate. Obviously, as I said, there will be not just one way. There will be several ways. Some are easily politically acceptable, others may not. So we want to simply put this information before the UNECE, various panels and so on, and take it on from there.
Yeah, exactly. This is what we discussed when we were also putting together the framework on carbon neutrality. So there is no one pathway. We will test with this task force. This is why we want to have those 5 dialogues with you to then get the output we are all happy with, and that we stand behind as a task force. And it is about now seeing what will come first out of the model in next 3 weeks when we provide the data we are all happy with. But all technologies will be tested, and then we will see what comes out. I think the fact that we have those couple of dialogues helps us as a team managing the process, but also you who are part of the task force to make sure that you help us to get the output with which you will be happy, and we will all be happy as a wider group. So I think we will this is like the first launch call, and we will continue working very closely together in our next 3 months while we get the outputs that meet or actually provide the messages that we want to communicate in our outreach activity in autumn. I see that Dennis wants to say something, and then I would suggest that we continue with our program. So please, Dennis. And then
so it's just a question on the energy intensive industries which are part of this carbon neutrality project, and what's the intention around whether you're going to model those in this program, or are they going to be left to one side? I'm assuming that you don't have a lot of data about where's the chemical industry, where's the steel industry, where's the cement industry, and what are the various cost curves for those people moving towards carbon neutrality. So what is the intention around energy intensive industries in terms of modeling is my question.
Okay, Dennis. Energy intensive industries will be effectively the next phase. We have industry as one almost homogeneous demand, and therefore also the supply routes towards are relatively limited. We are working on a much more higher resolution of the industrial, but also residential and transport sectors. But we will not be able to do this for the summer of this year.
Okay.
So that's sort of the next phase we have in mind. Right now, we will have to continue with some, and maybe you can help us there, sort of outside the model assumption and constraints where we simply say, thou shall not use more than this kind of form of final energy or whatever. That we can do, but in terms of a optimization and real accounting for, let's say, particular things like carbon use, reuse, and so on, or the whole hydrogen end use in the industrial sectors, that unfortunately we will not be able to do before May or June.
Okay. Well, just as an order of magnitude, I think BASF has just announced that if they want to move to some sort of carbon neutrality, they will triple their energy demand over the next 30 years.
Well,
that's the level of change that may come, and that's just for the chemical industry.
Well, that's information that is extremely useful when we get to it, and I hope that we can work with you, Des.
Okay.
Yeah.
Should we move on, Eva? Go to the rest of the presentation.
Yes, thank you so much. So again, we are here with an open door approach. So if there are any additional questions on modeling and specifics, please don't hesitate to reach out to me with direct questions or Holger and the team directly. We are really here to support. We of course rely on your support, but we are here to support also you countries, your agencies, that we get the most out of this exercise all. So I would like now that we start with the next segment of this call, and where we will be looking at how we are actually addressing the technology gaps which we identified in the Pathways project. And maybe Francesco, if you want to start first with hydrogen, then Behnam on CCS, and then Holger, if you can also share some thoughts on nuclear.
No, hold it. See, I cannot share anything right now. I don't know what's wrong, but whenever I say share, I get information and files from EASA's Teams connection where I'm not even close to it. So I would prefer if you could show the spreadsheets on CCUS and nuclear what we have, because it's probably easier, will be less confusing if we jump back and forth and nothing works.
Yeah, no, we will operate it, so you don't need to share the screen. I thought your reflection.
Okay, sure.
Let me do it step by step. So, Francesco, if you can start on hydrogen, and then we'll be Beckman. No worries, Holger. No pressure on technology.
Thank you, Eva. Thank you also for organizing together with Volker this call. So I'll proceed to share my screen. I see I have the rights to do so. Yeah, so I'll be presenting basically stylized flowcharts on representing, the processes that we have in MessageAX. As simple as possible, so everybody can be on the same page, and then possibly with a better idea of what we have, contributing to the Excel sheets that will be distributed after the workshop, and possibly also shared later on what we also have. So basically, I will focus on, as Eva was pointing, into the hydrogen production processes in our model MessageAX. And here you can find this flowchart that goes from left to right, starting from energy sources and CO2, going through the conversion steps, and then of course transmission, distribution, and storage, and finally ended up in the demand processes that we have. So yeah, as a starting point, I can quickly point you to the hydrogen conversion processes. We have steam methane reforming processes with and without CCS in 2 different versions. The same for coal gasification processes. And as we know, these 2 ways of producing hydrogen are mostly representing like 90% of how much hydrogen is produced today. So these are possibly the main processes here. And then we also have representation for biomass gasification with and without CCS. As an alternative and potentially cleaner, let's say, or greener way to produce hydrogen, we also have different electrolysis technologies, which can either be used for producing synthetic fuel synthesis, as we can see in this next on the next step, let's say on the right of the graph, or be used, of course, directly into the grid. So we also, as I was mentioning, have representation for the transmission, distribution, and storage message, and I think also answering to one of the questions of our colleagues, yes, we have a technology representing the injection of natural gas into the, injection of hydrogen into the natural gas grid, together with, technologies representing the distribution, so the piping using gaseous hydrogen, and also with liquefied hydrogen. Eventually, we also have technologies in the end-use side, mostly focused on the 3 end-use sectors, so residential, industry, and transport, with representation in the case of transport of fuel cell vehicles. In industry, we are aggregating the demands into electricity and heat. So it's kind of an aggregated methodology that we have, and so we have technologies representing those efficiencies, and also more or less the same in the residential through catalytic heating and also cogeneration systems. We also, of course, have trade in a representation in message, and we also have a refining representation. What I pointed here mostly in red color, so basically these 4 blocks are potentially processes or technologies that we are lacking some information, and we would like probably to be able to more explicitly model these. So I'm personally asking for anybody who's having in knowledge or possible reports or other studies of representing techno-economic parameters of these for processes to please share the data with us. For the sake of time, I could also focus a little bit more on the synthetic fuel synthesis that we also have modeled in message. And I'm not sure whether I should stop here and we could also answer some questions, or probably should go on with a little bit more detailed flowchart on these, let's say, synthesis processes or power to X synthesis that we have. I'm not sure what you think, Ivan.
Maybe it's better that you give your whole chat, and then there are a couple of reactions in the chat, and we will give floor for 7 minutes for reactions. I see that there are a couple of experts. So please carry on, and then before we move to CCS, Bechnam's discussion, we will have a little discussion Q&A. Thank you.
Thanks. So yeah, this is like a more detailed representation of these, let's say, blocks. I will shift back to just probably illustrate which block we're focusing on. And I'm basically focusing on this kind of greener pathway that would represent power to X technologies. So basically using electricity as the main energy source for producing different synthetic fuels, from gaseous as natural gas to hydrocarbons such as diesel or kerosene. So this is what the representation in a little bit more detail that we have. Basically, we have the two more different electrolyzer technologies, that solid oxide electrolyzer cells, which are a less mature technology that would present a potential higher efficiencies than the traditional alkaline electrolyzer cells, because they are able to use high temperature heat, which can be used from excess heat from the synthesis processes that we have here on the right. These four main synthesis processes that we have in message, basically representing the Fischer-Tropsch synthesis using syngas, the catalytic methanation, also methanol synthesis, and eventually the Haber-Bosch synthesis for producing ammonia. As I was saying before, industry is quite aggregated, so we are not, let's say, including specifically CO2 inputs from these technologies in here, but it was just an illustrative example of how the CO2 sources could be. And as a final remark, we also have in the model direct air capture, which is this basically also novice technology that can capture basically CO2 from the air, and we can either, of course, store that CO2 in caverns or depleted oil and gas reservoirs if we might to, but we can also use it as a byproduct, as a by-input, let's say, as an input for these synthesis processes that will all require CO2, except from the Haber-Bosch. So I think this is, again, a stylized and simplified flowchart for hopefully making our colleagues more aware of what we have and in a simple way. So thanks. I think that's all from my side.
Yes, thank you so much, Francesco. There are some comments in the chat from Mark, for instance, about the assumptions. You will see assumptions. You will receive an Excel workbook where you will see assumptions, and please, Mark, provide your input. It will be very helpful for modeling exercise. But there is one comment from John, maybe John Gibbons. Maybe, John, if you would like to turn on your camera or microphone and provide your comment directly to Francesco, so there it's rather substantive. On your first slide, Francesco, if you want to go to your first slide. Sorry that I make you to reshare your slide again.
Yeah, well, I had a few comments. Can you hear me?
Yes.
Yeah. So steam methane reforming. There's other ways to make hydrogen from natural gas with CCS. I'm not sure steam methane reforming with CCS will be used that much, actually. I've put a link in the chat to different options. I think people will be using autothermal reforming or POX. And then BASF, we're talking about methane pyrolysis, which might work in Germany where you can't get around to doing CO2 storage. So there's a lot more options. And I have to say, I think all this talk of green and greener, I thought we'd actually decided to be technology neutral. When it comes to that, that's one thing. And then in the bottom right-hand corner, you put CO2 coming in, but you don't say where it's coming from. and that matters a great deal. If it's fossil carbon, it'll just end up being re-emitted. So I think that's been quite. You do have CO2 from air, but is that so? Is the other CO2 fossil carbon then? Because I don't think you should treat them in the same way. They're totally different.
Let me interject before Francesco says something. You see electricity, high temperature heat, and CO2 that are inputs. Where they come from at that moment are not determined at this part of the
well, in that case, then, if they don't know where they come from, you have to count them as an emission.
Yeah, definitely. Yep. And I don't know if
that is a fair comment. Yeah.
But I think you do know where they come from, because I think you have a CO2 in an ellipse, which I assume.
No, we do know where it comes from eventually, but in order not to say presentation, we simply said CO2 in and leave it open at this moment where it comes from. Definitely, by the end of the day, when we do the modeling, we have to know where it comes from, and it will even choose necessarily where it would like to take the CO2 from. But if it's not from biomass or so, then of course we have to have a accounting.
Yeah, you do have a CO2 from the air as well, which is shown, which is good. But
okay.
Yeah, okay. But anyway, as I say, there's a lot of different routes people are talking about for hydrogen production with CCS, and steam methane reform work in some cases, but it wouldn't be your best bet in the number of cases. I don't think.
We talk about simplification of the real world, so we have to concentrate. We cannot have every way you can produce.
All right, well,
we have to think.
Let's see what the conclusions are of the simplification. And
no, that's why we need you guys to tell us which are the right priorities. We don't know.
We'll have a look at the final result.
Yep.
Yeah, thank you for your comment. Of course, the emissions are accounted for the synthetic fuels in case the CO2 is coming from fossil fuel-based processes. Sorry, Ella.
No, my apologies. I just want to say that this is why we are having this call, to brainstorm together, and this is why it's only task force for now, and it will be again only task force in 3 weeks or 4 weeks time. So this is exactly why we are having this call, and there are all questions, comments are now valid because we are still in front of the whiteboard. It will be late in a month, so better communicate what you're not unhappy now, not happy with now. I see that we have King making some comment. Was now this discussion also addressing to some extent, King, your comment? And then maybe Mark Howitt, if you want to have a quick comment, but we need to move to a CCS. So King, if you want to say something, unless, or was this discussion already addressing what you wanted to ask? We cannot hear you, King. I don't know if you're trying to say something.
I think Holger mentioned in the hyperturned heat. If that's included as a source, then that's fine.
Okay. So Mark,
sorry, Eva, just very quickly, just on answering on the previous comment on pyrolysis. Yeah, indeed, this is one of the technologies that we're looking information from. It's also I see an relatively new technology, or at least its potential is being recently reassessed. And yeah, we should probably have added like another red box here next to steam methane reforming and using pyrolysis from molten metals as an alternative, because it's supposed to be much more energy efficient. So just wanted to mention that, and we're also looking at it for that specific.
Thank you. Okay, let's hear from Mark, and then we will start now in 2 minutes with Beckham again. So Mark, would you like to say what you wanted to say?
Yes, thanks. I'm very concerned with carbon usage because there tends to be an awful lot of confusion sown. I think it's quite deliberate about carbon usage, because most carbon usage is putting it into, for example, synthetic fuels where it's going to be burnt and emitted. So therefore, it's not reducing emissions, it's delaying them. But then the carbon fuel, the synthetic fuel manufacturers say, oh, but we're reusing carbon, so therefore it's not a carbon emitting fuel. And therefore, by this sleight of hand of double counting, double counting the benefits and not counting the costs, it is treated as being a carbon reduction when it's not, it's a carbon delay.
Yeah, thank you. I totally agree with this. And of course, the maximum, let's say, benefit we can achieve is being carbon neutral. So basically, either using CO2 from biomass sources or from direct air capture potentially. That would be like the upper bound of being green for these fuels being green, let's say. So that of course, if we account for life cycle assessment, and I guess our colleague Toma will also talk about it, we will never have a purely neutral synthetic fuels, but of course will specifically delay, as you said, a lot. This, and of course it can be still useful for many hard to abate sectors in the end use. For example, we all know aviation and potentially shipping will be very difficult to decarbonize. So as a way of still supplying low carbon fuels to these, rather than trying to change some the technologies which are very, very challenging, it's some sort of a midterm solution. Thank you. I'll stop here though.
Thank you. Great. Well, then now after
point on that, please, just very quickly. Yes. If you're going to get if you've got direct air capture in there and you're making synthetic fuels with it, then you can just as well use the direct air capture to capture the emissions from using fossil fuels, and you can get less than zero emissions. You can go negative as well if you really want to. So there's absolutely no problem getting to zero that way if you've got direct air capture, and that seems to be a big emission. And most people would think actually if you've got direct air capture, then it's less cost to use it to capture the CO2 from the fossil fuels indirectly than to make it into a synthetic fuel.
Okay.
But then again, if you use direct air capture and try to put it underground, you've got the issues of the costs and the hazards in relation to the transportation and storage of that carbon dioxide.
Yeah, that's taken into account. The costs are usually reckoned to be pretty low. The hazards are probably pretty minimal compared to leaving it in the atmosphere. So I really wouldn't worry about that. I mean, I know you don't.
We had lots of discussion on that last year, and those costs and those hazards are grossly underestimated.
Well, so you say, but we're not going to sort that one out here. I don't agree. Very definitely don't agree. But anyway, I think there's a matter of consistency here that we have people proposing to make synthetic fuels with CO2 taken from the air, and that's inconsistent with not just using fossil fuels and taking the CO2 they produce out of the air and storing it back underground safely. So I think if you're going to do one, you need to do the other.
I would disagree. Why are you taking the carbon out of the ground in order to burn it into the air and then put it back into the ground?
Maybe you hadn't noticed, Mark, but that's what we're doing all over the world right now. You better ask people why they're doing it, but they're doing it, okay? And the reason I would do it that way is that it's cheaper, and it's going to cost enough to sort out global warming without going through unnecessary convolutions of ways for doing it. Using fossil fuel is done. It's why we've got the society we've got. If the UNECE doesn't want to accept, on the basis of one person's assertions, that storing CO2 underground can be done safely, despite the evidence that we've got that it can be, then we're not going to get very far.
It's Thank you, John and Mark, for sharing your views. It's good to have such frank discussions, and this will help really our project to get an edge. And we can go back to it also in our write-up, where we can go deeper and explain better what we believe it's the correct pathway. I see that Dennis wants to comment, so maybe yes, Dennis, if you wish, or maybe we do it when after Becknam's presentation on CCS. Is it something CCS related or?
No, it's actually about this debate that we've just had, which I
Please.
find, yeah,
Yes, then
because
go on.
it's quite fascinating, right? So the way this has boiled down to policy making in other areas is that you end up having a hierarchy of options, right? And the materials industry is very into circular economy, right? This project is about carbon neutrality, but it's clear that when you do direct air capture to synfuels, that's actually circular economy. So the question really is almost a philosophical one. Do you want to include circular economy to inform the policymakers of their options and effectively present a hierarchy of solutions from, don't use it in the first place, to circular economy, to carbon neutral? It's a proposal to clarify the discussion between all the technical experts. So that was my comment.
I think we'll have to reflect on it. I took the notes, so we will need to make a call what approach we take, but thank you for very valid comment. Unfortunately, we have to proceed now because we still have Becknam, again, Holger for a bit, and then Thomas has been waiting patiently. So Becknam, if you want to tell us a little bit on CCS briefly, and Holger on nuclear from YASA model, and then, yeah, thanks.
Yeah, probably, thanks a lot, everyone, for the interesting discussions. I might just bridge between this CCS discussion and the data template that we will be sharing soon. I don't want to go through that. I hope that you can see some of the rows here, but the way that we represent CCS in the model is that there are some retrofit or add-on technologies being added to existing, for example, gas power plants or other fossil fuels or biomass, and there are also some greenfield technologies that are built right from the beginning with CCS for capturing CO2 from different processes, not only electricity generation, but also fuel conversion and synthesis. And in this table that we will share with you, for example, I can just maybe show a couple of rows here that what type of data will be useful for us. We have a description of the technology or process that is, represented in the model, and what is the input commodity to that process technology, and what is the output, and what is the efficiency of the technology. It was the discussion about efficiencies and losses in the chat, so we will really welcome your comments and feedback on the assumptions that we have for the model. And of course, then it comes to technical parameters like capacity factor, lifetime, and the costs and the development of the cost over time. We have some projections based on assumptions in the model, but if you have some other projections, please let us know, and we will be happy to review that. Talking about the processes, I guess more or less I would say we cover main CO2 capture processes from fuel conversion and synthesis. And the area that probably we are a bit weak in the model is the storage and transportation. we are looking for data for example, for different UNECE subregions. What are the potentials for storage? What is the, for example, assessments of depleted fossil fuel reservoirs or some other potentials that they have, and if we can make this type of assumptions or this type of assessment that what is the maximum, for example, potential for storage, what is the cost of transportation, it will help us to represent this infrastructure better in the model. At the moment, we have a generic representation of CO2 transportation and disposal. So it's not, I would say we assume, for example, one cost for all the regions, but if there are, different distances and different differences, it will help us to refine our assumptions. That was from my side, Eva.
Thank you, Behnam. I see John has some reactions. Please, John, and Dennis, your hand is still up. I don't know if it's a legacy hand or. So, yes, John, please.
Yeah, so I didn't see in here anything on the amount of CO2 captured or the residual emissions. Was that one of the?
These are the input assumptions, and based on the scenario, for example, if we run some carbon neutrality scenarios, then we will see that, for example, how much CO2 has been captured in different years under that scenario.
You quote the thermal efficiency, but you don't quote the residual CO2 emissions that I saw.
Yeah, these are energy flows. These are energy input and output, energy content in the output fuel. These are not related to physical losses.
No, sorry, but I mean, we're looking at carbon neutrality. What are the residual carbon dioxide emissions that you assume from these processes?
You mean, okay, sorry, I didn't get the question right. Yeah, this model, the message model is linked with a climate model, with the image climate model, and the residual CO2 or other greenhouse gases in the air, they will be linked to the climate model, and then we calculate the temperature and the increase in the temperature based on different, for example, residual time. If that was
sorry, I'm not making it clear. So all of these processes will still emit some amount of carbon dioxide when they're running. All of these CCS processes. What is that amount? What are you assuming for that amount?
Yeah, the amount that this CO2 processes, this is far right to the right columns in the table, that how much they can capture. This is taken into account the fuel input and how much that has been captured, and the capture inefficiencies, how much has been released to the air. And yeah, coming back to your question, this also helps us with the discussion of carbon neutrality, that how much we want to see, for example, residual, how much overshoot, this type of, I guess, different scenarios will be also interesting to discuss.
Yes, because that's a number that can be varied, obviously. We've had this and some comments, but I mean, people are looking very seriously at capturing 95% or more. And if it mattered, you would capture more, it would be economical, rather than using direct air capture to get it back. I also note that you've got some negatives, which implies that you're making an assumption about the life cycle emissions for biomass, I guess.
Yeah, those negatives are exactly for those are for scrubbers. That they just use electricity. These are retrofit additional technologies. So it's a little bit different. They don't have any fuel input. They have electricity, and they capture a share of the released CO2 from that parent technology.
Interesting way of looking at it, but okay.
Yeah, thanks.
And there was also...
I guess we need to look at some of that, but I think certainly the capture level is by no means fixed. you can vary it. And people have been stuck at 90% or lower for a while, but it didn't seem a very good reason why they were doing that.
Yeah.
And it's much. I think if people are doing it seriously, they'll basically go up to the level where it's cost effective, ceases to be cost effective to capture on your plant, and becomes cheaper to do air capture. But that's quite a high level of capture. That's in the high places that cost will switch over.
Yeah.
The other comments I got, which does actually go back to what Mark was saying, some places it will cost you a fortune for transport and storage of CO2. In other places it will be very cheap. It's quite variable even within a single region. So I don't know what you do about that, but that's the nature of it.
I'm sorry that I need to interrupt. There was one additional question. I suggest
maybe I just make a short comment and reply.
Yes, please.
Just also for other experts, I guess we have this convenience in the model that we can represent different technologies. Like for example, here we were talking about capture rate with the advancement of that technology over time. Or, for example, depreciation of the technology. For example, if we install it today, after 20 years, how much will be capture, how much will be efficiency? These are the things that we can represent conveniently.
Just as a comment, the standard for the UK is likely to be 95% for the first plants being built. So things are moving on quite rapidly because of net zero. Anyway, yeah. But what would you do about the variable? It's site-specific CO2 transport and storage. What would you do about that? Presumably, we can't do it any more than we can do the transmission grid. Exactly.
Yeah, because the spatial resolution of the model is quite aggregate. So we need to come up with some either processing or some additional modules and models. We usually do that. For example, for power system, we use data or empirical studies or other models that they can refine our assumptions, because the integrated assessment, the global model is quite large. So we have to do some compromises and try to, usually it's a challenge to choose the best strategy.
Yes.
And if I may inject, and we do sensitivity analysis. If we are unsure about data or we get conflicting input from experts, then we use simply one run with A and one run B and one run with C. So we see how much impact these changes have on the model. And then we can say, well, actually, it doesn't make so much difference at a global scale.
Yeah, but for the example of transport and storage, what it means is, for example, those cement plants that can have access to CO2 transport and storage, it's quite cheap, and for the ones that can't, depending on where they are, it's very expensive.
You already see
it's heterogeneous
with country by country data on some assumptions I used from Wolf Heiduk and my own on the storage capacity, and I ask for the average distance you may see, or the range of distances from the source, the power plant or whatever the capture is, to the storage, and we have as understanding of the transportation distance. So that is material you'll be getting from either.
Yes, the whole package will be shared. Yes, the whole package.
I don't think that will get you the effect. In other words, half the plants are at greater than average distance, half the plants are below, half of them get retrofitted, so, and half of them don't. I mean, it's that kind of situation.
Yeah.
Because if you take the average distance,
better than nothing. And for us, what I know about some of the countries, nothing, no location, nothing, and we need that kind of feedback from local experts.
Well, I guess all I can suggest is that, particularly for that one, you may want to come up with a way of doing it, which just says what fraction of the fleet in that area is amenable for CCS. It may not be all of it.
Yeah, that's
much
more than we have.
Yeah.
Maybe
Okay,
Holger, now, if you would like to continue and tell us a little bit more what approach you will take for nuclear, addressing that gap that we identified for nuclear energy approach. And then let's see if maybe colleagues who have expertise in nuclear power would like to share any thoughts. And then I would like to give floor to Thomas so that he has also another 30 minutes to share and seek some feedback. So Holger, if you would maybe now we start talk about a little bit about nuclear power, what we
since I
what we
can't
have
share
and what we do.
anything, let's please verbally explain. We have two nuclear technologies in the model right now, and we is for, of course, for a nuclear dive and higher resolution way too little. So what we would like to have is, first of all, technology-specific data. The way Beckham has shown capital, first of all, operating costs, and so construction time, construction schedule is extremely important because of the interest during construction being a major cost factor and so on. We also would like to have input from more innovative reactors at the small modular scale, particular for issues like high temperature heat. You saw this slide from Francesco for the hydrogen production. We have a high HT red, that high temperature that would come from a SMR, for example. And all these kind of things we would have to discuss, see what can be done in terms of not overloading the model. We have in each of the technologies or each of the dive, and we have to be selective and prioritize. And do we need to model, let's say, the nuclear fuel cycle? I don't think so, but the experts may have a different opinion. Now that this kind of issues we have to discuss. We would also have to see a better breakdown than what we usually use for the fixed and variable operating costs, in particular, as much as this decommissioning and final waste disposal is included. Now, if you want to do anything on the fuel cycle, that we have to seriously debate and see what can be done, because that would also mean major changes to the model. We have some rudimentary approach in it, but which can pass muster with nuclear experts. So that's basically what I can say right now without having my material.
Thank you, Holger. Yes, we will share the very data-heavy table on nuclear, all the nuclear power-related inputs, and it will be part of that package that you will receive by tomorrow. Maybe if King, Philippe, or David, if you have some reactions now, I don't know.
Yes.
Yes.
Thank you, and obviously we're very much happy to provide you with the data. And obviously, I would say, from what Holger you presented, we can provide data in two camps really, because one, nuclear power plants is already operating, and they are potential to extend the life of existing power plant. And we can have data for new build existing large reactors, which are projected costs. Again, we have a firmer basis. And Holger, you mentioned about new technology. So again, obviously, those are not only pilot plants are being developed. So they are projected future costs. So obviously, compared similar to other technology which are under research and development, so we only have estimated cost for those. But I think with, again, and we have data for waste disposal and so forth. They're only a small part. But I just want to check, as nuclear would include the waste disposal, would that also be included for all other technology to make sure that we have make sure that when we look at cost that we're comparing like with like? And I think by just one last point, I think following up from what Mark mentioned, that we are looking at the total system cost. Obviously we can provide individual technology cost, but ultimately what's important to policymakers and consumers at the end is the total cost that be bared to them. So is that going to be flagged up that with a particular pathway, what is the total cost to make that energy system work?
Okay, we will certainly show the investment flow between various approaches, various scenarios, and so on. We will also be able to show certain impacts on prices, on shadow prices in particular, of different approaches, scenarios, and so on. Now, just that we all understand, we will not be able to distinguish between a light water reactor, boiling water reactor, and so on. We use a relatively generic approach because the model can't, it's not a set degree of detail for any of the technologies, nuclear or otherwise, is not possible in a model, in a global model as we have is 14 or 15 regions. Then is computationally not possible. But if we can sort of work together to come up with this kind of generic technology characteristics and performance profile, that would be great and could be helpful. Also, we would have to do some kind of thinking about constraints. Some of the models or regional approaches are constrained simply. It's not part of their policy to use nuclear power, let's say. How can we sort of argue and make a case that nuclear power, at least in a scenario, and not in all scenarios, but in a high nuclear, would also penetrate those markets and regions? That's something where we also have to come to a common approach.
Great, thank you. There are no immediate reactions. Any additional questions? Thank you so much to YASA team for walking us through this, explaining us how the model works, reminding some of us, and also telling us what the approach will be for those technologies that we identify gaps last round with the Pathways project. I would like now to give floor to Toma, and thank you for your patience. So now we are moving to next segment, and Toma will spend some time to share with us his approach that he will take for a life cycle assessment of a range of technologies. So I think I gave you power to share the screen. Yes, perfect. Toma, floor is yours.
Thank you, Eva. Thank you, everyone, for being here today. Now we would like to talk about life cycle assessment, but focusing mostly on the electricity generation technologies. So that means excluding hydrogen production and usage, for example, and other things we talked about previously. But hopefully this is still relevant. Does it work if I put it in full screen? It should be the other way around. This way, I think it works. The starting point of this work is actually a report that was published a few years back by UNEP, and to which I contributed, and by the UNEP International Resource Panel, which was a broad-scale comparison, also multi-regional and with scenarios of electricity generation technologies. So we included coal, natural gas, with and without CCS, hydropower, wind power, concentrating solar power, photovoltaic power, and geothermal power. And we focused on impact assessments for the period of 2010 to 2050. Of course, we have calculated greenhouse gas emissions, but I will show you after a bit what was included. Just so we're on the same page, I wasn't sure, so I included this, but I'm sure all of you know about life cycle assessment. It's both a method and a tool to attribute environmental impacts to products and services, considering all the impacts over the life cycle. So from production, use, end of life, considering also resource extraction, transport, production of emissions, waste, and anything that goes back to nature in a sense. So we call that first principle the holistic principle. And typically, life cycle assessment does not really care only about greenhouse gas emissions, but also about any kind of impacts that we are able to measure. That's an important point as well for the system at hand. So we end up with a list usually of hundreds or thousands of emitted substances, and we translate that into indicators. So we also have this multi-criteria dimension to life cycle assessment. So what does it what does it involve for electricity production? For example, for a wind turbine, you will start with extraction of raw materials, production of parts, transportation, construction, also operation and maintenance to get into account, and then the production of your kilowatt hour delivered to the grid. And some end of life management. If that happens, then you also can take into account some recycling. And along this life cycle, you add all the emissions of anything you can account and translate that into one type of impact, so grams of CO2 per kilowatt hour, basically. So in this UNEP report, we ended up covering these technologies and have pretty much a picture, environmental profile of each electricity production technology for 2010 and 2050. So you have this profile for different indicators from climate change, freshwater ecotoxicity, freshwater eutrophication, toxicity on humans, also material depletion, and some others. Here it's compared against the global grid of 2010. So you can see that since most of the grid of 2010 relied on coal power sticks very much to the 100%. But for the more new technologies, you see variable profiles, mostly, for example, wind power and photovoltaics, which tend to have let's say, an overflow of metal depletion because you use more materials per kilowatt hour delivered, but you also have co-benefits to decarbonization because you end up with lower particulate matter, lower photoaccident formation, lower toxicity. For ground-mounted photovoltaics, you still have a bit of land use, but anyway. This is from a publication that was actually after the UNEP report, so nuclear appears here, but it was not included in the UNEP report. This is actually very much based on a lot of generic data, which is something that ends, I think it's quite old right now, and that would need quite an update. And some other results you can have, I can't remember who said that there's no zero emission technology, but yeah, it's definitely true for all of them. You probably know most of this data also from the IPCC reports, that greenhouse gas emissions per kilowatt hour can also vary a lot across technologies, but also across time and regions, which is all in the report, but we won't spend time on that right now. There are also other things we can talk about, so we can calculate human health impacts, for example, or ecosystem impacts due to different type of effects that are then converted into more rough, let's say, aggregated indicators. Yeah. We can also couple the LCA work with scenarios. This is not something we plan to do now, but I thought it would be interesting to show what we end up as a conclusion, showing as a conclusion in the UNEP report that basically we show that phasing out coal has a lot of co-benefits, but there are some trade-offs in terms of material requirements. So it's important to remember as well that in this work and this work that we're going to do for the next few weeks and months, we will also have scenarios included, but not to calculate the global impact, but rather to model the technologies themselves. So we have a lot of technologies that require, for example, high amounts of electricity for production, for example, the silicon in photovoltaics. And that electricity will vary in terms of composition, depending on the region where you produce the photovoltaic panel. So we would need also some support from scenario modelers. Anyway, the context. and what we and starting from that, what we can actually identify as limitations and things we can do better. So first, as I said, there's an absence of state-of-the-art nuclear power and biomass modeling. So we need a lot of expertise on these technologies. We started already the work with our colleagues that I saw in the chat from WNA, but for other technologies, it would be really good to have state-of-the-art data on efficiencies of power plants, assumed lifetimes, and any kind of material compositions for different parts, for example. For the power plants that use fuel, it would be also good to have an update on how this fuel is made and where it is actually sourced in the world. For uranium, for example, it matters a lot. So yeah, then we also have some limited considerations of other things we would like to have in LCA now, such as methane leakage in fossil fuel extraction for coal and gas. So if anyone has any info on that, that would be great. We did not consider direct emissions in hydropower because it varies very much depending on latitude and depending on the kind of valley or reservoir that you're actually flooding. So you have a lot of biogenic CO2 or CH4 emitted for hydropower. If this is something you know or you have an idea where to find the data of, that would be really great. And the energy scenarios we use in the UNEP report are also some energy scenarios from the IEA from 10 years ago. Now we have the possibility to use other large-scale scenarios. So we started some work also on coupling IAMs with LCA, which would be great if we can also have a chat, maybe a part of that with the EASA colleagues. That would be quite nice. So a lot of possibilities. We don't have a lot of resource. The most important is really to update the lifecycle inventories. And as I will mention just after, and also something that Holger, you mentioned, that we will need some more data and more technology description for the small modular reactors, for example.
Okay.
So this is the first step approach really for the next weeks and months, really updating the lifecycle inventories. So my aim is to circulate also Excel sheets among experts for you to comment on assumed deficiencies, different lifetimes, energy consumptions. I'll show some examples just after, before I circulate the files on these technologies. So you may also notice that we include carbon capture and storage. I'll give you a bit of a wrap on that just after. The second step is to include these small modular reactor technologies. So we have 3 technologies we'd like to model, which might also be of interest to you, EASA. So also another point, we might need to convene. And then, as I said, but I would like to insist, is that at the end of this task, we will provide a per kilowatt-hour life cycle comparison. I don't think we have the time or resources to upscale or to actually be able to say in 2050 the total amount of impact, so it could be greenhouse gas emissions or land use or anything, of technology deployment will be such or such, because you have to take into account different pathways, also the regionalness of the different deployments. But basically, that could also be a good idea to, maybe later on also to discuss how to do this, maybe later on if EASA is interested. And at the end, of course, we'd like to propose a report with all the data in there. So if there's any question at this point, we can already start, because then I will switch to the files probably.
Oops, I don't know if you can hear me now. Maybe it's better. There was one question from Dennis. What's the geographical approach? UN aggregate level or sub-regional level? That was one question. And then I see that John has his hand up. So I don't know. Actually, I'm also curious. I forgot about the geographical approach. We need to take UNECE. So if you can maybe tell us a little bit more. And then I will give floor to John. I see that John wants to react.
Yeah, I mean, obviously, the full life cycle emissions need to be taken into account but if we're proposing to deliver net zero, then you have to deliver net zero. So picking up on the point Mark made, although slightly differently, you do have to pay for your residual emissions, and you have to pay to correct them by taking them out of the atmosphere. So I don't see where, for example, you're allowing people to put that in the whole sort of cycle of their activity, because that is, that's the only thing we could do. If we want to get to net zero, if you emit CO2, you've got to take it out the atmosphere again. There's no other option. You can't pay, it's no use paying money to the government to do that. Net zero just implies getting net zero.
Yes, I agree with that. I think the only negative emission technology we will have in the portfolio is BECCS, and that would be the only one that could really just.
No, that's not satisfactory.
Yeah.
You need to include direct air capture. I mean, you've got Oxy building a 500,000 ton a year direct air capture plant. If people are going to be serious about net zero, they better sort out direct air capture.
Do you think it has the potential at scale to capture gigatons of CO2?
Oxy Petroleum, who are not, despite what some people would say, they're not stupid. They're obviously trying to preserve their business, but they're talking about building a 500,000 ton per year direct air capture unit in the Permian Basin. So yes, I mean, BECCS will run out of biomass. No question about that. Direct air capture, you just pay money.
So how do we include that because the scope for now?
I think you put it in with a range of sensitivities to cost, but the scale is potentially quite large because you can do it anywhere in the world, which helps a lot with transport, CO2 transport and storage. And there are a number of different technologies being developed. But the cost, pick a number. It could be anywhere between probably $100 a ton and $500 a ton.
Okay, if the technology description is available somewhere, then yeah, that would be great to have.
There are multiple suggestions. There isn't a single technology. You've got a lot of different options, but the fundamental thing is the cost, and to some extent where you can do it if people or. But I don't know if that really figures in our calculations. But very definitely, there's as much as we've got to put it this way, I think you'll actually sort out direct air capture sooner than you'll sort out the advanced biomass gasifier that you've proposed. I think it's a lot easier actually. So as I say, it's a technology that makes it, if you don't have it, be very, very hard to get to net zero because, as you say, everything emits some CO2.
Mm-hmm. Yeah. Okay, so I guess that would be possible if we can have the model itself, like what it takes in terms of transport, of infrastructure, then as long as we have that.
At least, you see, one way you can do it literally anywhere in the world. So you probably end up putting it where you've got a combination of whatever energy sources it takes to drive it, plus secure geological storage. That might be the American Midwest. Might be the Middle East. Might be some places around the North Sea. Yeah, and other places. That's not an exhaustive list by any means.
Okay, noted. Then if I happen to find some literature on life cycle assessment of DAC, I could probably try to add it. Yeah.
John, would you have some interesting sources that you can share with Toma to help?
Yes, there are sources to be shared, but as I say, it's an interesting situation. We're talking about the future, which is always hard to predict. And there are multiple ways of doing things. I don't quite know what we're going to do on that, but we are looking forward with a number of different things. And I think you've got to look forward with direct air capture, but direct air capture is, if you like, it's the technology which has no other purpose but achieving net zero. But it is, it's coming from a very sort of, it's very behind everything else because people haven't been taking net zero seriously for very long. I can give you some information, but I can also guarantee that it's an area that will change significantly.
Okay.
Thank you.
I would like to repeat, Thomas, a question that was really focused on your methodology and approach. So from Dennis. And Dennis, please interrupt and jump in if I'm misinterpreting it. But for your life cycle assessment database, what's your geographical basis? Granular in the UNECE, and I trust you here mean by sub-regions, Dennis, or is it an overall average?
So for the UNEP report, the regions considered were the same as the classification of the IEA. So we have 9 world regions, but I don't remember exactly which ones. It's North America, Latin America, former USSR, Western Europe, Africa, Middle East. So it's 9 world regions. The reason why we need regionalization, as I said, is first because we need to adapt to the different electricity mixes that are expected in the next decades in these different regions, but also for the production that depend a lot on climatic conditions. You need to adapt the hours of solar radiation per year or these kind of things. But apart from that, that's where the regionalization stops. So we don't have, for example, we don't have what could be. We don't have extraction of materials that would differ in one region than from another. For example, the extraction of of iron ore would be the same in all regions and use the same in all technologies. So we have a 9-region resolution that we could imagine we could also match to the regions that of UNECE.
Great. I don't know, Dennis, if you're happy with this answer. I just want to encourage Thomas. There was you to check chat. There was quite a bit of interesting sources you shared here directly in the chat that might be useful. So there are no any additional now immediate questions, no hands raised. So if you would like to proceed, Thomas, and
yes, actually, maybe so there's one point we will need to improve. So first, I can also show you first what kind of assumptions we make in the UNEP report, if anyone could react to, for example, plant efficiencies for fossil fuels. I don't think I'll take much time in the Excel files either, but it's always the wrong one. Because I think we, in the UNEP report, for example, we have...
Can you say what basis the efficiency is on?
Yeah,
you don't know whether it's higher heating value or lower heating value. Makes a big difference.
That's a good question. I think it's lower heating value. It's all from NETL reports in the US.
Well, it's probably higher heating value if it's in the US then. But
okay,
it does. It really matters.
Okay, then I will check that. Because one thing I found is that since the UNEP report, for example, I have a slide on that, but fossil fuel efficiencies seem quite low in the UNEP report, and it's something I would like to check probably with you. That, for example, it's coming back from the beginning. This one. What we found in this report is that without CCS, for example, coal would be under 900 grams of CO2 per kilowatt hour in total, so in a life cycle. And I think it's really low considered newer research on the right, where we show that the 1,000 kilogram CO2 per kilowatt hour, 1,000 gram CO2 per kilowatt hour is pretty much reached for all power plants in the world. So I'd like to know whether you have, anyone has good vision of that. It's probably also linked with inclusion more and more now in LCAs of methane leakage. So I think there was also some questions on that. And that's something I would like to add to the inventories. So I see, for example, Mark, you mentioned that methane leakage is not restricted to fossil fuel extraction, but also throughout the distribution and usage system. Yeah, that's also what I found. But thanks for that. I will check and see what I can add in here. Let's see.
I mean, that people talk about methane leakage from hydroelectric schemes as well, don't they?
Yes, that's also another one. But I have one on methane leakage here. It's not going on the right screen, sorry. But basically, yeah, we don't account it for don't account for it for extraction and transportation. It could actually be quite significant.
It's pretty variable. I mean, there are things you can do to avoid methane.
Yeah.
People pre-extract methane in some places, but and different coals are very different. I mean, it's hard to get consistent numbers, but it's not looked at enough. I agree.
No, yeah, it seems to be quite significant for some types of I think this publication on top is for natural gas, but they say that for extraction, for example, it accounts for 50% of the impact GWP. And also, of course, if you take the GWP over 20 years, it's even more because methane has a higher global warming potential. Okay, so I will look into that, and if anyone has good sources, I see that some posted some in the chat, so I will keep that in mind. And same on hydropower. I think I put it somewhere else. So this is what we found somehow, but that we didn't include in the result is. My PhD supervisor at the time tried to do some correlation between latitude, size of the reservoir, and depth, I think, to estimate CO2 and CH4 biogenic from the hydropower reservoirs. So if we have something close to that, it would be great to add, because it seems to be few of the big gaps that are in the UNEP report right now that we would like to have considered. Was there other methane emission? Great, okay. So everyone has documentation on that. And thanks for the LCA of the direct air capture. That's I'm going to look at that. Yeah, Climeworks. Okay, I know what they are.
As I say, that's one example, but there are other radically different technologies.
Okay, that's great. Yeah. And then David, you commented on the capacity factors for power plants here. Yes. Yeah, that was the assumption that we had 85% for most of them. It's highly likely that in the next years, we hope that fossil fuel power plants will probably be needed less and less with penetration of renewables. And so, yeah, this is something we can make assumption on. It doesn't really matter in a sense because the capacity factor really helps to calculate the impact of building the plant. Not so much in terms of direct emissions and also from the upstream of the fuel of the coal. So it will really be, but I think it's something to consider as well.
Thomas, there is one hand up by from Mark. So I don't know if Mark would like to react. He also wanted to react before. And sorry, Mark, that we continued with presentation. We didn't give you a floor. So yeah, if you want to now comment, please.
I had a few comments. I'll put them in the chat. One of them is about nuclear power stations. That's in your modelling. A nuclear power station delivers baseload power. Renewable energy delivers intermittent power. So to get intermittent into baseload, you need large-scale, long-duration storage, but you also need 3 gigawatts of wind plus that storage offshore to make 1 gigawatt of nuclear, or 4 gigawatts of onshore wind to make 1 gigawatt of nuclear, or 6 to 10 gigawatts of solar plus that storage to make 1 gigawatt of nuclear. That's one issue. Another issue is the land usage, because you've got an energy density per square kilometer of about 64 megawatts of wind per square kilometer offshore, about half that of solar or onshore wind, and yet nuclear you've got about 5 gigawatts per square kilometer. So that's one issue on nuclear. I've also mentioned various other discussions in the report. For example, we've got to compare with business as usual. If we only look at the costs of the energy transition, all the headlines will be, look how costly the energy transition will be. If we look at the costs of business as usual, we discover that there are 20 times as much subsidies going into fossil fuels as there are into renewables in the developed world, and much more than that in the less developed world. So all we need to do is redirect existing money to renewables, and that totally changes the headlines.
Yeah, I agree on the investment side. But that's not something we will consider in the RCA. But I totally agree. On the land use, it's actually been a bit. There's been a lot of heated discussions whether wind turbines actually occupy land or not. For example, in our study, we included the wind farm land, but of course, this can be multi-purpose land, and so whether we take into account the space between the wind turbines or not as being allocated to the production of power is a different discussion, I guess.
Well, there are two aspects of that. One is what you can use the land for. Well, if you wind turbines, you can't use the land for cities because of the noise and the interference between the buildings and the turbines. You can't use them for prairies because they get in the way of the combine harvesters. But you can use them in conjunction with, say, fishing and dairy. On the other hand, there's the visual amenity. People don't like them in their backyard because they're unsightly. And that's a very important and understated thing that can't be financially qualified, but is very much affected by this land use consideration.
Yeah. Yeah, I agree. Yeah. But yeah, so far we just chose to allocate the lands. It matters quite much actually in the end, because per kilowatt hour the rest is really small because it's just material production. So we'll see what we can do. It's easy to add or remove later on, but it's a matter of choice what we do for wind power. And yeah, so we talked about fossil fuels. Then I had hydro, wind power. Yeah, for photovoltaics, we chose to model silicon-based, so it's monocrystalline and polycrystalline. Actually, it's not only polycrystalline, but I also have data for monocrystalline if that's necessary. And thin film photovoltaics, so we have cadmium telluride and CIGS in the database. Thin film technologies are they're still, I think, emerging, because commercially most of the technologies is polycrystalline, but they have much lower impacts per kilowatt hour, because pretty much you skip the step where you have to use a lot of power to produce to make the silicon. And the assumptions for photovoltaics, efficiencies are here, and there. I'll put in full screen if you want to have a look. So in this one, which we didn't really do for the other technologies, we also consider the improvement in the technology itself from year to year, not only the fact that the background electricity is changing. For example, the efficiency of the module would increase quite significantly to 2050. And that's why, we found results that were really low, like under 10 grams per kilowatt hour for photovoltaics in 2050. Also material efficiency, basically the layers will be thinner and all of this was quite up to date at the time. It was 2014, but we could probably also rely on the latest from NREL in the US.
Thomas, there was one comment from King, which
Yes.
is in a way linked to, now my chat disappeared, related to this post. So I don't know if we have seen it, but does the LCA data include waste and disposal of all energy sources?
Yeah, no,
Yes, your methodology.
It's true that not all of them include the end of life, and that was the case in the UNEP report. We would need to have end of life treatment, basically recycling. So recycling we have for photovoltaics, but we didn't take into account recycling for wind turbines and for hydropower, and none of that also for fossil fuels. So end of life treatment will also need to be added. That's a very good point for these technologies.
Okay. I'm also conscious that we're already reaching the.
Yeah, sorry, that's right. Yeah.
But do you still have a lot to cover, or are you?
No, that's fine for me. So the files I would like to circulate quickly, they look like this. So I'll show the one for example, for coal without carbon capture and storage. And they have, it's pretty much a list of things that go in and go out. So I can spend some time with people who are interested to go through the files, or I can also try to just disclose the key parameters, which is what is probably preferable. But for those who are interested, we just have a model of what is emitted per kilowatt hour, what is needed in terms of, for example, of coal, how much coal you need, and how much other consumables you need for operation, and actually for different phases of the LCA, but we don't have time, so yeah.
Thank you. So yes, as we mentioned, we will compile all those all that material, and you'll receive a package tomorrow, and then we will have you will have about 2 weeks time to revert back with any data that you wish to be reflected. We really kindly ask you for your help because now this exercise is very, very important for anything that we do next. And I don't know, Thomas, do you mind if I share now screen? Okay, thanks.
Go ahead.
You read my mind. You jumped out. So I just want to share one last slide with you to explain. So you will receive package with data with tables, which I don't know if you can see now the screen. And we kindly ask you to review it, to provide us with any sources or directly input data that you might have at hand. And the process will take now next, let's say, 2 weeks time to, and work with package will include what's listed here in a little post-it. And then next steps, as I mentioned in the beginning of the call, will be that we will have a preparatory task force call sometime mid-May. And then first consultations later, end of May. We really, I need to reiterate, we really rely here on your help and input, your expertise and input that you can provide us. So I will extend invitation to provide input and comment not only to people who were able to join the call today, I thank you very much, but to the whole task force. And also I will put this recording, I decided to record the meeting on the website for people who missed the meeting, as well as with all the slide decks that were shared. So it will be shared also for wider community, but staying within our task force for now. I will be in touch tomorrow or Friday morning, and if you can help us and revert back with data, that would be hugely appreciated. We really count on you, on your expertise, technology background, the regional geographical background, and I think this really will make the project, it will give it an edge and our outputs will be more robust. So this is what we are all after. Okay, there was quite a bit of also discussion in the chat. I will download it and I will also share it. I'll try to see how to maybe convert it in a document that we can share, because there's a lot of great references and thoughts that can be and should be documented. And we can also include it probably in the package or on the website. I will see how far we get. The package is now something that has to go out. You will receive it. I don't know, are there any immediate reactions? No?
Well, I just
yes.
added a small comment to the chat. It's just if we should probably should set up another communication channel besides simply emails. I'm not sure if you had that in mind. Probably, you know, because we will need more iterations, right? And that could become very tricky to just handle.
Yeah, very fair. This is a very good point. Thank you, Francesco. So we will do it like this way. I will be point of contact. I will share the package that I will receive. I have received quite a bit already from YASA colleagues and from Toma, but let's see tomorrow morning if we're really happy with that package. This will go to the task force, and I invite experts to then provide me the feedback, which I will then channel to YASA colleagues and colleagues from the list. So if would that work with all of you? And then if there are some specific questions, we can always maybe have another round of communications, but we would prefer to stay here at the Secretariat as a contact point between our modeling organizations and the task force, so that we can have it all documented, because we will need it for the reporting once the project finishes. Does that work for everybody? No objections? Yeah? Okay. So then I think we all agreed. Yeah, thank you. We will be in touch. Thank you again for your time and patience. And this is an exciting activity, actually the most exciting, I think, part of the project. And we will be soon in touch. So yeah, next call, I would like to schedule it for, in a month time. But for now, we are looking forward to receive inputs from you.
Bye.
Thank you. Bye.
Bye.
Thank you, Eva, for organizing.
Bye,
everyone.
Thank you.
Thank you, Eva.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.
Thank you all.
Thank you.
Thank you so
Bye.
much. Bye.
Bye, everyone.
Bye. So I don't know if maybe Francesco, Holger, or somebody.
Thank you.
Thank you. Bye bye.
I'm from Azerbaijan.
Bye bye. Thank you.
Bye bye. Bye bye. Ha? Görüştün sen de.
Francesco, can you hear me still? Hello.
Bye bye.